Okay, see, today we are going to talk about a topic of ship controllability, BDT, or you may say this maneuverability. Well, this is the American spelling, this is the British spelling, okay, EUR and OEUVRA. I am just writing because we may change one to other, so that we have no confusion. Basically, these things are more or less same topic. We are going to be discussing this part of the ship behavior, which is related to, you may say, maneuvering, controllability, course keeping, etc. Everything related to a ship trying to move in the horizontal motion, in the horizontal plane. Earlier I spoke about more of motion in the vertical plane, that is under wave action, but here what we are going to talk about is that sea is calm, there is no waves, etc. Ship is moving and it is trying to turn. It is trying to, when it moves along a straight line, you study the subject of resistance, but here we are trying to find out how it turns. Should it turn? What forces is necessary to make it turn easily, or what should be the characteristics so that it does not turn for a simple simple forces, external forces, or if it has turned because of a wave or some disturbance, should it come back to its original line. All these things are a part of what we call maneuverability, controllability, and these sometimes they are kind of, we have to understand at the beginning, contradictory. A ship which is highly maneuverable means very highly, you can turn it very easily, becomes less controllable because it is always trying to turn. It is just like your scooter or a vehicle which is always trying to turn, and if you want to make a steady course, you have to hold it tight. So there is two kind of aspects again. I mean, if it's something is, it is a tanker going on a straight line, you cannot, you give a rudder, it does not turn. It's absolutely having a very strong directional stability, but then it is not controllable. This is the part we will talk in general. Before that, let me tell you about this, why the forces come. See, again looking back at that. Now what happened as you try to turn a ship? See, when you are going on a straight line, the force is symmetric. There is no force coming in y direction, no moment coming in this direction. The force is absolutely along x direction only. So the ship is moving exactly on a straight line. But here what happened, as you try to turn, naturally there is a asymmetry developed. The ship is not symmetric anymore, as if it is having a motion and the flow is coming in this direction. And then what happened, obviously the flow goes various ways and there will be a different set of pressure, and therefore there will be some kind of force coming, some kind of movement acting on that, and it is that which will cause the ship to turn. In other words, the only mechanism that you have to cause force on a ship which is not restrained is fluid forces, because of the flow, because the way the flow going past it. These are the forces that will cause it to turn. You see, you give a rudder, what happened, you change the rudder, but what happens, because you change the rudder, the flow past that develops a different pressure system, and that is why there is a force. Why I am saying that is because in order to study controllability and maneuverability, we have to necessarily study fluid forces, because it is that forces which will cause the vessel to turn, or whether the force is very large, etc., will decide if the vessel would remain steady. A simple example is given by this weathercock stuff, which is what I will just briefly mention. See, suppose there is a initial trajectory of a line and there is a particular, like small line with a what you call a large tail. Let us say there is a small thin plate with a large tail here, and the tail is such that is the one that produces a force. What happened? It is supposed to go this side, but now it has turned. By some means it has actually turned by an angle psi. Then what would happen? that would obviously cause, even if it is going on a straight line, the flow was going past it, but now the flow is going past, I am just considering this part of it measure, it is going to give some kind of a force on this direction. This force is equal to, if let me say Cg, this force is equal to this force plus a moment. You know, any force can be translated back to another point, or rather this force will give a moment about this center point, let us say Cg point, this is say Cg. Okay. What it does therefore, this part, this red part of the force will cause the thing to move up, because there is a force here acting on the Cg, so it is going to go up, and this moment will going to make a turn like that. So, you will expect the vessel to actually, I mean this body to actually gone slightly up and then begin to turn. As it turns, now think of that, as it turns this angle becomes small. So, at some point it has moved up and then begin to turn. As it turns, this angle has become small. As it becomes small, the force becomes less. So, ultimately there will be a point when the force has become 0, so it becomes straight line. So, therefore, the behavior is guided by the fact of how much force is coming on that, which depends on obviously angle of attack, which of course will keep on changing as the angle of attack reduces. So, as an introduction, we have to realize that we have to study the forces coming for a general body moving in a horizontal plane. If we want to understand even the elementary maneuverability, later on of course we must talk about rudder. What does rudder do? Okay. The most common mechanism for keeping the ship in course is a rudder, as we know, and if you want to turn, you might have an additional device like both thruster or thrusters on the center plane, etc., etc. In other words, you have to introduce a force from external mechanism. That will come later on, but to do that we should understand what kind of force come on the body. Let us go to a very basic definition of what is called course keeping. Okay. Now, there are certain things that can occur for a course keeping. First of all, let me introduce the word directional stability. And various definition of directional stability for a ship. What kind of stability the ship might possess? Obviously, you would want a ship to have it should be stable as well as controllable. As I said, highly stable is less controllable or less maneuverable. Yeah. Now, the very basic definition of the word stability, as I mentioned, we have talked that in an earlier class, is related to the fact that if on a body an external disturbance acts for some time and cause the body to have moved from its original position of equilibrium. Now, if you have removed that force, should the body come back to its original position of equilibrium? Should it stay where it was, or should it keep on deviating? This is what the standard definition of anything called stability, which is the classical example is given by this sort of a hill with a ball here. This is obviously unstable, because moment you change it, this is the equilibrium position, there is no force and moment you change it is going to actually go away from that. So, it is unstable, it is deviating. If you give a momentary disturbance, it deviates from its state of equilibrium. You keep that here, it is neutrally stable, because you shift it here, it stays there, and here this is stable. Similarly, for a ship, you would expect that it is going on a straight line, maintaining a direction. Now, you give a disturbance, so it has changed its heading. Should it come back to the same straight line, or should it keep deviating, etc., etc.? That would be the concept of directional stability. Same concept, you have a state of equilibrium, which is in this case a ship moving along a straight line. You give a disturbance which might have come because there was a sudden gust of wind or whatever, and there is always a wind coming trying to cause disturbance. On that, does it keep deviating this way, that way? This is actually a concept which is very valid in many cases. If you think of those old days, I remember my younger days, there used to be this corporation car for dirt. There will be an engine with number of bogies. That when they go in a turn, it go like that and everything follows behind that. Even there is a concept of directional stability, because if they are not directionally stable, there is a design consideration. Then when it turns here, you see along that, one bogie will try to go this side, other will try to go this side, other will try to go this side. But it does not happen. You see that when it turns, number of those bogies, just follow it. This is also same as directional stability. So, it is connected to the fact of whether it actually follows a path. Okay. Now, let us see for a shape what are the possible definition of directional stability. You can have two or three actually kind of cases. There is a shape here. Always we are assuming that it is going on a straight line. Now, what happened? You give a disturbance. There is some kind of disturbance here, some disturbance there. So, the ship can go along. It gets disturbed here. Say it gets disturbed here, whatever. And but when the disturbance goes away, it follows now another straight line. It can have that. Okay. Or if you have given an angle here, it can actually goes in a circle. But that is not very common. Say this is what will be called straight line stability. Okay. Now, you can have another case when there is a shape here supposed to go in this line, you give a disturbance. So, what happened? It gets disturbed, but ultimately it goes to this line, along this line. Okay. It can have this. This will be called directional stability.
Like a disturbance we gave, so it moved on. The second one, this disturbance is how
I will tell you. This actually can also happen in two ways. If the disturbance is given, it actually comes like that and goes like that. See, okay, the second case, ship is going in a straight line. At this point of time, there is certain disturbance given. That means, suppose you have pushed it, a wave came and gave a big push. It has now changed direction. Now, what happened? It can follow now a path which is going like an oscillation. It has introduced some kind of oscillation, but even see the disturbance is given in one moment, like a bang you have given and removed it, let us say, just for demonstration purpose. In reality, it will be for some time. So, it can introduce an oscillation, and then actually ultimately when the disturbance goes, it actually follows a straight line parallel to the original straight line. Okay. This would be means what? It is maintaining direction after the disturbance is over. And here also there can be two cases. Normally it can actually, the disturbance would have caused an oscillation and then it goes to a straight line, or it could have simply deviated that and it goes to a straight line. These two are basically, both the cases are example of directional stability, but the mathematics of the forces differ. One can tell from the hydrodynamic characteristic whether it will be this type or that type, whatever. These are directional stability. The third one is that going on a straight line, you give a disturbance here, so it actually goes to this thing, but ultimately it comes to again straight line when the disturbance goes away. So, in other words, in case 1 you have disturbance when it is given has caused the ship to go along a straight line after you have removed it. Okay. So, it is having a straight line stability. In all these cases, it is possible that when you are given a disturbance, it simply goes to some other direction, then it is unstable ship. Supposing a ship cannot be controlled, there is a disturbance there, it simply introduces some force, and in fact what will happen, it actually goes larger and larger, then it is unstable ship. We are not talking of that, I am talking of the definition of various kinds of stability that a ship have. Instability is obviously when a disturbance is given, you remove that, it simply goes wherever you have no control, then it is unstable. We are not, I mean that is obvious, so I am not discussing that right now. Now, supposing it is stable, what kind of stability the ship may possess is the question. So, it can possess like this, it can possess like this, it can possess like this. Now, now I tell you that this too, this can be called positional stability. The ship can have also position, it maintains the same line. Now, remember, a ship has no restraining force. So, if I have a ship is going some place and you have given a disturbance, it is changed heading, nothing can bring it back if you have not made a correction. So, if you have an autopilot or a helmsman, or rather if you have no rudder, you cannot have this situation, because if you do not give a rudder correction action, you cannot maintain the heading, you can only have this stability. In other words, a ship without any control, this is what is called control fixed. If you do not have a control surface operating, at best what you can have is a straight line stability. In other words, you have a rudder frozen, okay, just ship is going, you give a disturbance, it takes another direction and it keeps going on a straight line. That is the best you can have for a ship if you do not give rudder, because obviously when the ship has changed its heading, there is nothing to bring it back. The ship was going on one line, it suddenly become this angle, you cannot bring it back to unless you give a rudder, but at least what happens, it is maintaining this straight line. This is what is called straight line stability, which is control fixed. These two are possible only with the rudder acting or autopilot acting. On that also, you see, because otherwise when the heading is changed, you cannot bring it back to the original line, but so these two are basically acting with rudder or autopilot. So these two are kind of stability. Now normally what happen, initially we will be discussing about obviously the characteristic of the ship's inherent stability, because this part is connected to the hull. You want to know whether the hull has an intrinsic stability property, because if the hull is of this type, then it is much easier to control that with a rudder. See, if the ship tends to give a disturbance, tends to go this way, you can correct it by rudder, but you need really much more rudder action. You have to continuously make moving the rudder. Most ships you see, especially larger tanker, primarily goes along a straight line, and only if you make a turn, you will make a turn with a large circle. So large ships, you do not need very high maneuvering, quickly following, that you might need for a petrol craft or something. So this is the one that we will be talking little bit initially, and try to find out what is a characteristic necessary to ensure that the ship possesses straight line stability, which of course can be done only in control fixed. Of course, I can also tell you that many ships in reality do not have straight line stability or have slight lack of straight line stability. There are various measures of extent of stability, because they get corrected by this. You can also see that if the ship is very strong straight line stability, that means it always wants to maintain a straight line, then it is difficult to turn it.
It means that the rudder is fixed in one
Yeah,
direction,
yeah.
not moving.
Yeah. This case,
First case.
yes.
Or it does not have a rudder.
Or does not have a rudder. You can say the controls is not operating, you may not have a rudder. So that means that this is guided by the kind of forces are developing on the hull itself, because it has got turned. See, the question to answer is that there is a disturbance, it has caused the hull to turn. The turn has caused some forces. These forces that has got created because of the turning, should it diminish with time or increase with time? We would want it to diminish with time, so that it becomes a like it does not just like in our hydrostatic stability. I give it a heel angle that possesses a moment. That moment, does it cause the heel to reduce or increase? Okay, that is what we want to. Only thing is that there I had a hydrostatic force setup, here I have got a complicated hydrodynamic force setup. Okay. So now therefore I need to talk little bit about this equation of motion type of thing. So we will talk about that, although I frame that as a next lecture, but then it is a combined topic. So we understand that essentially for ship maneuvering, we are looking at the ship motion in a horizontal plane. You can say surge, sway and yaw, those three motions, that is on the plane where there is no restraining or hydrostatic spring force, nothing is holding it back. That is what we are talking about now. So what I need to do is that we need to actually come up with a kind of equation of motion. After all, why equation of motion? You see, equation of motion tells me mass into acceleration equal to force. I have to find out, if I have given a force, it has set up an acceleration. So it has have a velocity, have a displacement. Does the velocity and the acceleration reduce with time or increase with time? That is what we want to investigate. Therefore, we have to have an equation of motion. We will not go through the detail, but I will try to tell you what we normally study. So, when we want to do equation of motion, obviously you have to define an axis system. Okay. So, I will try to draw this as quickly as possible. Okay, let me say keep somewhere here. This drawing takes little time, that is why I am trying to first draw. Use various colors, it will be easier. Oh, I should have done this. Let me just draw that. You can just follow it little bit. See, okay, we will now go through that. First of all, let us say that we are going to only use xy coordinate system, because we are thinking that it does not have any motion in the z plane, although in reality there can be such little heap, and if you want to talk of submarine you will have, but we are talking of ship here. So, I have a global coordinate system O x0 y0. This is my earth or inertial okay. What we are trying to do is that how do we define the ship's motion in the horizontal plane. Now, I have got a ship here and I have got a center of gravity here. Normally what happens nowadays, it is the path of the center of gravity, which is this blue line, that is the path of the CG. That is defining the path, where the center of gravity is moving. In fact, it was the same thing in sea keeping also. Now, I have a body coordinate system that we are defining here as G. Let us use this thing x, y, and see this is the path. Therefore, what is the velocity? Velocity is obviously tangential. This line is tangential to this line. See, this line is a tangential to this path line. So, at any point obviously the ship's G has a vector this way, tangential to the path obviously. That means here the ship is moving in this side, but having a heading angle having an angle. Now, the various definition that comes in, see no other color is there now. Okay. See, first of all, I can draw another line here which is parallel to this x0 y0, that is a black line. This line is just parallel to that. So, now I have defined a axis system xy on the body. So, gxy is fixed on the body. So, gx is the longitudinal axis, gy is your starboard side. Okay. Standard fixed. This is what when you are sitting here, you are seeing x is your the bow and y is your on the side. That is what you see. This is my reference line fixed on the globe. So, my heading angle is this angle, what it makes, that is what we call heading angle. Actually, normally in navigation you talk in terms of heading 180 etc., where you would have decided that with respect to another frame of reference, perhaps with a art system, like longitude, latitude etc., but that is different. You have a reference line here fixed on the earth on the shore with respect to the ship has a heading angle. This angle is what is called the drift angle, because what happened, the ship is moving this side. So, the flow comes, you can see if you are sitting here, you will think the fluid is coming this direction to you. Fluid is coming this direction to you, making an angle of what we can write beta here. Drift angle, or one can say also angle of attack. So, you see what the velocity vector makes with the x axis is a what is called drift angle or angle of attack, because that tells me which direction the flow is coming to. In fact, the fluid force depends on only that, whereas heading angle just tells me the heading angle, or you can say this is heading or yaw, heading is same as yaw, that tells me which direction it is heading, right. And I have got of course this x y system here. So, you know, if you see this vector is this to this is going to be y o of g, this one, because this is y 0, this is x 0, this is my g point. So, what is my coordinate of g? Y o g is how far it is from the origin, and obviously this much is x o g. This is capital X. Okay.
Heading or yaw is that angle.
Oh, okay. No, let me write this separately. Yeah, let me make it small x. Sorry, let me make it small x o g. Let me make it, because small y o g. Let me make it y o. Let me make it x o, because I am going to use x 0 y. See, again I will explain. I mean, this was only a question of nomenclature. I have got O x 0 y 0, which is the earth fixed system. I have got G x y, which is fixed on the body. Okay. G is the center of gravity. So, where the G moves with respect to this earth fixed system tells me where the ship is located. So, the ship is located, say, so much, you know, say y direction, so much x direction. That tells me where it is located on the earth's surface point. There is the coordinate point, and obviously its heading angle is given by where is x axis located with respect to this. In fact, this is nothing but actually the you may say in a sense sway, surge and yaw. This is actually sway, this is actually surge, and this is actually your heading angle. You only need this three. You do not need here roll, pitch and heave, because they are on the other axis system. So, here I have got x, y and a moment about this axis going to the vertical. Okay. So, this definition should be very clear in the mind, because many things depend on that. So, you see when the ship turns, this is a very common thing. No ship can ever turn when it is going exactly, a path line is same as heading line. You have to have an angle of attack beta. When the ship turns, you know that it turns like this, as you know, you all know, it cannot turn like a car exactly following like this, it just cannot turn, because no forces can be produced if you turn that way on the y direction. So, you cannot turn like that. What I mean is that you cannot have a turning here when the ship is exactly parallel to that. You have to have an angle of attack. Okay. Because why? Because without angle of attack you cannot have the force on that. So, I will come to that later on. That is an interesting part, unlike hard or any other things that you will find, because here there is no external force, the only force is fluid forces acting, that cannot act unless there is an angle of attack. Flow must come with an angle, because if the flow did come from this side, there is no force on this side. If the flow came on along x axis, there is no force on this side, that would be like a ship moving on a straight line. Now, what we need to do is to find out equation of motion. What does Newton say? Force equal to mass into acceleration. So, I must find out force equal to mass into acceleration, F equal to m, you know, into acceleration. What is the acceleration here? This I will now we have to refer to this equation number of times, but let me say that I had this the Newton's equation basic form. We will not go through much of this equation. I want to, as I said, we will try to contain that, to just bring out the essential features, not really work out the equations etc. to that extent as you you know, I mean we won't make it complicated. See, it now we call here, looking at that, we will call the force coming. Now, I have to write the force. So, I am going to call the force coming in this side, the force, remember, as capital X 0, that is what we are, and the force coming on this side as capital Y 0, and the moment coming like this will be moment n. Now, this now n I am not calling n 0 etc., because whether the moment is about this vertical line, which for xy system and x 0 y system is same, because this line is same whether it is g x y or o x 0 y 0, because it is of this plane. So, it is n straight, but never mind the n part. So, we have this. Okay. Now, why I am writing that? You see x0 should be equal to mass into this is x0 is my force in this direction, is mass into acceleration in this direction. What is the acceleration in this direction? Is double derivative of this distance. So, I can write x0 equal to m into xog dot dot, y0 equal to m into yog dot dot, and n equal to I into psi dot dot. I am just going to write that and then this thing. So, we can say x0 equal to m is the mass, okay, into xog dot dot, y0 equal to m into yog dot dot, n equal to I into psi dot dot. This is my Newton equation motion in global, earth, whatever you call, or inertial system. Okay. Okay, this is my global or earth or inertial system. Again, coming back to this, we have to refer to this many times this way. Now the question comes like this. See, what happens is that this is a very sort of simple algebra. Now, you do not want to find force on this line, because at some point the ship is making an angle of say 10 degree. Next time it may be making an angle of 20 degree, next time maybe 30 degree. So, to find force along this line is always difficult. See, at one point that you just think the logic again, the physics behind it, why we want to change it to another system, because if the ship was going along x, just by inspection, it would be so much easier to find the force along the small x axis and small y axis, because small x axis the force would be the resistance force and y axis will be the force along the say you can say sway direction force, because sway direction is defined as that. That way what happens, it is not depending on the geometry, instantaneous position of the geometry. It depends on the geometry for a particular hull but for a given hull it will not depend on geometry anymore if you are defining the forces along the body system, because the body geometry along this g x y is not changing with time, whereas the body geometry about this one is changing, because today is like that, tomorrow is like that, tomorrow is like this. Okay. So, therefore, it would be so much easier if we want to define all the parameters and equation of motion in along this line. That means, I want to find out what is my force here. This force here is mass into acceleration. So, let me call that the velocity this side is u here, if I want to take a velocity here, and velocity here is v here. See, if I now this v was a vector. So, I had a velocity this side some, that is x o g dot, but I can let me define this velocity as to be small u, right. I am defining, I am calling that the velocity this side is small u, velocity this side is small v, and rotation of course remains same, which will be psi dot, which I can call r. Normally it is called r when r equal to psi dot d psi by the rate of change of this heading angle. We will come to that afterwards. Okay, I will come to that little later on. But understand this, that let me call this to be x, this to be y, and now I am going to call the force on this side to be x and force on this side to be y. So, what we are doing, think of that, there are two systems. One is that along this line I have got a velocity which is xog dot. You can say okay, if I want I can call it to be u dot velocity, and I can call this to be v dot as velocity. Okay. So, I have got here u dot. Again we go slowly. Along this line, earth axis, I have a velocity u dot which is equal to xog dot, you know, the d by dt of xog. I have got velocity v dot, v0, I have not v dot, v0 which is yog dot, and I have got a rotation which is obviously psi dot which is r, I am calling it r. R does not change because r axis is, remember, vertical axis, rotation about this axis. Now, similar, and the forces I am calling here is x0, y0 and n. Similarly, I am defining here now small x, small I force as capital X, capital Y, velocity as small u, small v. Now, I have an equation of motion which we just, where did we do that, where I have got in earth system x0, y0, and these are in earth system, this is earth system. I want to change it all to body system. That means I want to write this thing in terms of u and v and r, and this thing I want to write in terms of x and y.
So R, small x and y.
No, the forces are small capital X and Y. See, forces are capital X0, capital Y0, and so and X and Y. So all the O system, let me put it, the suffix O refers to earth system, and small xy are the coordinate, and big xy are forces. Okay, and y r is nothing but psi dot is nothing but your velocity. That is invariant whether it is x0 or y0. There is no r, see there is no r0. If you call r0, then r0 is r, because the rotation is a velocity, you see, and this angle psi dot, the rate of change. See, for example, it was, let me say that it was 10 degree and it is rotated, next second it will become 11 degree. So it has changed to 1 degree per second. Whether you are referring with this axis or that axis, it is 1 degree per second. So r, the yaw velocity, the reason is because yaw velocity is the rotation about this axis, this vertical axis. That is same whether it is here or here. Okay, this is why there is no change in the yaw velocity. So I need to now basically make a change of these equations from this axis to that axis. All right. Now I will not go to this much detail of that, but what I will try to tell you here, looking at this, that it turns out that if you have a system here x, y, and if you have got another system x0, y0. See, if you have got here something as say x0, y0, O, and you have got x and y, and if you have got an angle psi here, and if you take any point here, it turns out that, see, if this vector, okay, let me write in a different angle. If this is a vector, okay, this is x, some vector. So if you take this vector in this coordinate system or that coordinate system, and you call by different name, you know, x or x0, or you can call it also x0 bar, it turns out that the coordinates in one is related to the coordinate in other by kind of transformation. That, in other words, you can say that x in system 1 can be related to a transformation matrix into x0 in system 2, and similarly x0 r, it becomes inverse, but inverse is transpose, become x0. Let me not get into that so much, but I will just give an example that what happen, our x force and y force will become, this will become equal to cos theta into x0 plus sin theta into y0. This will become cos theta into y0 minus sin theta into x0, or I can write, see, it becomes like that. This is a very simple coordinate transformation. I am just trying to think if I should explain this term in more detail. Okay, let me say I am trying to explain this in more detail. Okay, see, this is a vector. Okay, this is a vector of a point P here. Now this vector is, when I am representing in terms of coordinate x0, y0, then this becomes my x0, this becomes my y0. So this is my x0, this is my y0, and when I try to express that in the other coordinate system, this distance becomes my y, and this distance, that is, you know, well, you can say this distance becomes my x. So this is my x, this is my y, this is my x0, so y0, this is my x0. So this is my x0, this is my y0, this is my x, this is my y. What it says is that by coordinate transformation, it mean is that how do you express this in terms of this and that. In fact, we have done that actually, if you recall in our cross conceptuality, this becomes nothing but this into cos psi plus this into sin psi. The x 0 cos theta, if you know, in this case say this is theta here, let me call, we are just trying to tell about a general transformation. If you have represented a vector in an axis system and same vector in another axis rotated by an angle theta, then how they are related to each other? They are related by a simple transformation like this, very simple, and in fact you can write in a vector form. If I want to put that, I mean if I just neglect that, this becomes actually cos theta sin theta minus sin theta cos theta, this multiplied by x 0 y 0. This is actually so elementary that we need not actually talk so much, but what I want to say is that there is a very standard fixed relation available to transform one axis to the other axis. Okay. Now, what we are doing is, see, we are now going back to this again equation here. Now, we have got x 0 y 0, we need to transform them to x y, and here we have got acceleration. In fact I can write this term as u 0 dot and this term as v 0 dot. Okay. I have got here u 0 v 0, but with a dot. So, I have to first change x 0 y 0 in terms of x y, and I have to change u 0 dot v 0 dot in terms of u and v. Okay, the two things are there. I will come to that in a minute, in maybe systematically here. So, you have got here, see, x 0 y 0, this turns out to me r of x y. Okay. And when r equal to we have said this r actually is the value like this is RT according to our definition, or rather x y, we found out r of x 0 y 0 when r is given by cos theta sin theta minus sin theta cos theta, something like that. These are all standard. Okay. Now, think of this. Now that is very simple. Now, I can always go back to this this equation, and I can write x 0 y, instead of x 0 y 0, I can write them in terms of x y. See, I can write x 0 to be x cos alpha plus, like I can write this x 0 as I have mentioned here in the previous slide. I mean, I can just do the opposite. I can write x y in terms of that, or x 0 in terms of the other one. Not a big problem, you see. So, I can basically express x 0 y 0 in terms of x y or x y in terms of x 0 y 0. Let us say that I understand. Now, we need to understand a little bit of u and v, that is a little more complicated. See, I have got u here, u 0 and v 0. These are also vectors, velocity vectors in which axis? In R6. That will become obviously here r, which is, let me write it out in terms of this thing, cos theta. Actually, this is cos theta minus sin theta and sin theta cos theta into u v. Okay. I will expand that little bit. One of them, say u 0 becomes u into cos theta minus v into sin theta. Now comes the ball game. Now I want to do u dot. So, I will start with this. This is a interesting point. So, I have got, see, u 0 equal to u cos theta minus v sin theta. Okay. So, what happened is that we have got this u and v terms properly. Okay. But now if you look at my equation of motion, I will just bring back. My equation of motion is x 0 equal to mass into u 0 dot. Okay. So, I have expressed that in terms of x y. I have expressed u 0 in terms of u and v, but I want to find out what will be u 0 dot in terms of u dot and v dot. I must try to find out what is u 0 dot in terms of u dot and v dot. Now, you see from this equation, if you do u 0 dot, What is this? This is d by dt of u0. This is going to be d by dt of u cos theta minus d by dt of v sin theta. Why I am writing this? Because this has two parts. Cos theta, theta angle itself is changing with time. So, I have got here cos theta into du by dt plus u into d by dt of cos theta.
Both are dependent, u and
Okay, like that. Now, if you do this d by dt of cos theta, you get two terms, because I will come to this I am not going to the exact mathematics. Now, I have got here see, one term was cos theta into du by dt, one term u d by dt of cos theta. Okay, I have got that. Now, what is this? This is u dot cos theta, because du by dt is u dot, straightforward. But what is this? This is u. Now, d by dt of cos theta is d by d theta of cos theta into d theta by dt by chain rule. This is equal to minus sin theta, and what is d theta by dt is theta dot. What is theta dot? It is your velocity. So, this becomes minus u dot cos theta minus u r sin theta. What is r? R is theta dot equal to your velocity. What? Okay, this is all complicated maybe to some of you here, but all that I want to tell you, never mind this mathematics, all that I am trying to tell you, when you are changing an axis system, this to this axis, remember that this axis is rotating, this axis is not fixed, this axis, this angle is changing. So, there is a rotation of the axis. Because of the rotation of the axis, an additional term appears depending on the rotation r, rotation velocity r. That is all I want to know. This is what is called actually lateral acceleration, one can call Coriolis acceleration, various terms are there. Whenever you are having a rotating system, system itself is rotating. If it was not rotating, the r will be 0, so you end up getting same sin theta cos theta part, but the system itself is rotating. So, you think of a point here. Now, this point, this vector is not just simple one, but tomorrow this is changed, because the axis on which you are actually defining itself is changing. So, the principle that is important here to understand in your mind is that when I take acceleration vector, then I have got an additional term, because there is an additional rotational velocity of the coordinate system itself. This coordinate system itself is rotating at a velocity theta dot. See, I am defining with respect to ship coordinate system a point, but that point, the coordinate system itself is rotating. That gives rise to an additional acceleration term. This is what we have to know. We need not sort of go through the detail now, all that, but you see what I will tell you, that that this equation, force equal to mass into acceleration. Now, if I rewrite all that in terms of x and u, what I will end up getting, see, in other words, I have got this equal to this into x og dot dot. If I rewrite that, I will end up getting this side as x, this side I will get mass into u dot minus v psi dot, and I will get y to be mass of v dot plus u psi dot, and n of course remains same. See, this is what I will get. Now, here I will tell you, earlier it was x equal to mass into acceleration. See, x0 is mass into acceleration, no, not x0, sorry, x equal to mass into acceleration. Here also x into mass into acceleration, but the acceleration is now, yeah, okay. Now, no longer just u dot, but u minus v psi dot, because this part is arising because of the fact that the axis is rotating. This is a very common thing in any rotating system. You go to a rocket or something, it is much more complicated, more terms, but this term arises, which is very important, this v into psi dot, or you can say v into r, because of the fact that the axis is rotating. Obviously, if it is not rotating, my psi dot will be 0, and if it is 0, it is mu dot. Okay. So, I will we will pick up from that. This is simply what we have done is, we are still on the introduction part, you may say, all we have done is we are writing Newton equation of motion, mass equal to force into acceleration, but now I am defining the forces and the accelerations and the velocities all with respect to the ship system. That means, it is the u is the velocity along the ship's instantaneous x axis, which is itself changing. and because of that you get extra terms. So, we have end up getting this equation of motion, which will be the starting point for our next part of lecture, simply by writing equation of motion with a moving body fixed coordinate system. That is all. Thank you. Okay, we will continue on this equation of motion in horizontal plane. See, we had this equation just in the last lecture. I just write that V into psi dot and y was m of V dot minus plus I think u into psi dot and n equal to I into psi double dot. Okay. Now, you see there is one thing that is that modification we can do on this is that sometime what happened, these equations are written when the axis was a center of gravity, g. Okay. Sometime what happened, it is easier to define that when the for an arbitrary axis system somewhere else here. See, here I have taken this equation of motion are taken where the body system is having its axis as center of gravity, but sometimes supposing it is having an axis which is some other location O here, so that the center of gravity is the coordinates are xg and yg. Okay. In other words, I define it with respect to another coordinate system, then certain extra terms come in. In fact, it simply gets modified as I will just write down that some extra terms will come in here, or rather let me do it in a second one. Let me draw it here. This is my g, this is my x, this is my y. But if I took a axis in a general sense somewhere else with this to be the coordinate axis, so that this is my xg and in other words, if I took, let me put it, if I took a body coordinate system somewhere else, so that the center of gravity has a coordinate of xg yg, in other words you can say center of gravity is say 5 meter forward of the mid, say I took a midship. So, center of gravity is 5 meter forward of midship. The reason is because sometimes some of the definitions are easier for a hull with respect to a geometric fixed point than the center of gravity. When you are defining lines plan, you are better off taking midship as the origin point, not xg, isn't it, not the center of gravity, because center of gravity can be 2.354 meter forward of midship. So, it becomes difficult. So, as a result, if it is easy, if we want, we can choose the body coordinate system as some geometry point and then say that center of gravity is xg meter forward of that, yg meter starboard of that. This is a very important and interesting part of that. So, what I end up getting is therefore is that I end up getting that y force becomes equal to delta v into dy by dv plus delta v dot dy by dv dot plus delta psi dot dy by d psi dot plus delta psi double dot dy by d psi double dot. Okay. This is what we end up getting. Now, here I want to have to say something more at this point of time. Now, you see what is my delta v dot delta this thing, these are actually the small changes. Now, there is no point of writing them as delta v, because after all initially you see I have a v velocity of 0, now I have got v velocity of small value of say 0.1 meter per second, but that 0.1 meter per second is a change in v and I call that delta v, but I can also call that as a v itself, because after all the ship was going at a velocity here without any sway velocity. Now, I have got a sway velocity, small number regardless. So, I can call that as, instead of delta v I can call that as also v, because delta v makes it more confusing. So, I can call directly this as a v. So, I can call that as a v of dy by dv, because when the v is understood to be a small number, A ship cannot be, see, a ship goes at 10 meter per second here, it cannot go 10 meter per second this side. This side is only small number, it can only be a change with respect to the 0, and that I changed initially to illustrate that we call delta of v, but see, in other words you can see this way, v equal to v 0 plus delta v, but v 0 is 0, therefore delta v is v. So, whatever small number you get is the sway velocity. Okay. So, I use this nomenclature because delta v is no point of, so whatever sway velocity I get, small number is the change of sway velocity because my initial sway velocity was 0. Initially I had a 0 sway velocity as well as yaw velocity. Similarly, you will find out that I can call delta v as v, delta v dot as v dot, delta psi dot dot at delta psi psi dot dot, and delta psi dot at delta psi dot, or this is actually r. Set up v and r, v dot and r dot, and those v and r, v dot and r dot have set up my forces. Now this force equal to motion. Now I want to see this equation of motion will tell me the solution of that forces that velocities that was generated because of some disturbance, which in turn generates a force. Does it generate a force at an increasing order or decreasing order? Because if that force, think of a loop type, for some reason I have given a v. Now this v gives me a y force. If this y force is such that this y force increases my v, then it would have made my v larger. Then this v would have made my y even larger, that y would have made my v even more larger, it would have been unstable. But if it is the other way around, I have gotten v which produced an y force. This y force is in such a direction that it tries to reduce my v, then that v would have become little small, then the y would have become still smaller, then that would give me my v even more smaller, it will go to 0. So, this is what is called the study of stability. That we will talk next class, is given by the characteristic solution of this equation. Here I have got v dot r dot and all these coefficients. I want to know v dot r dot, do they grow with time or do they reduce with time? I have to see, and my shape would be stable if they reduce with time. This is exactly why you need to find out the forces. We could have done that ship is stable, unstable. We cannot do that in this case for the very simple reason that the forces are necessarily created because of the velocity and acceleration, which are fluid forces, and it is the force and the velocity interplay that tells me whether the ship is stable or unstable. So, we will pick up from this point, and next class study the property of or the characteristic of or the requirement for a ship to be stable. From the solution for that, we will not go to the detailed solution, just some preliminary ideas. Okay, I will stop it here for today.